Thank you very much. And I thank all the organizers for a great workshop, and well, and all of you for coming. So in my talk this morning, I will be talking about the emergence and significance of an attractor in heavy ion collisions, and I will start by saying a few words about the early time puzzle in ultra-relativistic heavy ion collisions, which is the context in which this arises. And by way of introduction, I will describe the simplest example of such an attractor in Müller-Israel-Stewart hydrodynamics, and then I'll move on to somewhat newer developments in this area, which concerns the attractor in RTA kinetic theory. So I give a reference there to the paper where that's described. And then finally, to a study where an attempt is made to introduce transverse dynamics into the Bjorken setup, which is where the first two parts will be situated, so to say. Okay, so first the early time puzzle. So this is a question which comes about because MIS-like theories, which are formulated in the language of hydrodynamics, but are in themselves not hydrodynamic, are very successful in their application to modeling quark-gluon plasma created in heavy ion collisions, and this application is puzzling because the situation described is far from equilibrium, so we are far from the hydrodynamic domain, and of course MIS is not QCD. So the question is, why is this working? And it suggests the emergence of some kind of universal behavior, and this cannot be hydrodynamics because this theory is then far from the hydrodynamic domain in the sense that the constitutive relations of hydrodynamics are not well satisfied there, and so there's it's at this point just a word. A pre-hydrodynamic attractor is presumably emerging, which is some kind of universal behavior earlier than one would expect it, because of course at late times we do expect let's say the solutions of the system to gravitate towards some submanifold in the full phase space of models used to describe this, and this submanifold corresponds to perfect fluid hydrodynamics, basically. But earlier on, we wouldn't expect it, so something is going on here. And one can speculate, this is not really known for sure, but one can speculate that this attractor is due to a confluence of special circumstances which characterize heavy ion collisions. So in other words, we do not believe that Müller-Israel-Stewart theory is just a surrogate for QCD in any circumstances, right? There is something going on in a heavy ion collision that makes it work. And I've listed two factors here, which I think I think everybody thinks are important in this problem. The first of all is a dynamical statement, which is the boost invariance of particle production in QCD. So this is easy to call a kinematic constraint, but it's really a dynamical constraint. It's some information. It's information about what QCD is like. The second factor is the dominance of the longitudinal expansion. So the collision takes place along some axis, and the medium created is expanding mostly along it. There's little transverse dynamics going on, and so that sets the stage for the Bjorken model, which was formulated in the early 80s, which idealizes these plus possibly some other assumptions, and that is the context in which the emergence of an attractor is most easily seen. Well, I just mean that when we read phenomenological descriptions of heavy ion collisions or even experimental papers, basically they always refer to a more or less standard pipeline. Yeah, I think that's what I mean, yes. I think that's what I mean. I think if it didn't describe the data, we would probably not have this conversation. Yeah, I think that's what I mean, yeah.
I mean, are there observables that can be described unique in terms of your, so perhaps the photon production? What are the observables that allow you to think about only the
As far as I know, I mean, I may not know, but as far as I know, the only thing you can really get out of the Bjorken model is an estimate of the energy density early on based on, well, that model plus probably some other assumptions. I mean, basically, you need to also assume like something about how much entropy is produced along the flow and so on. So it's I don't think there are any real observables, right? So I think so at the end today, I mean, I will be describing precisely a way to address this this conundrum. I mean, everybody who loves and enjoys Bjorken flow on the daily has this feeling that, you know, this is this is wonderful, but it's actually not answering the real questions. So I will describe an attempt where Bjorken flow is taken as the zeroth order approximation in a way, in some kind of theorist's vision of a heavy ion collision. So this may or may not be, you know, natural from the point of view of someone who actually solves like MIS equations on the computer. But I mean, from a theorist's point of view, it seems like Bjorken flow is capturing something. And well, I don't want to give my talk now. I want to give it in a second when I give it, right? But I mean, it does tell us, it does give us a metaphor for what is going on. In other words, it suggests that there is something going on that's not hydrodynamics, that's not really QCD. One would want to say it's actually really kinematics, but then an essential element is boost invariance, which actually is not really kinematics. So anyway, there is something that follows, but I agree with you. It is more sort of a sort of conceptual warm and fuzzy feeling that you get, that somehow you see why, you know. But as far as physics is concerned, I don't think the Bjorken model in itself is giving us that much. But I do think that having a conceptual picture of how information is propagated along the flow. I mean, I will say lost sometimes, but I don't mean lost, of course. I just mean suppressed. I think that is useful, and also one can try to include these transverse dynamics to some degree, taking advantage of the second point that initially this is a small perturbation to Bjorken flow. I mean, this approach encounters problems, but it's not entirely hopeless, and that will be the last part of my talk. Okay, so I'm assuming everybody's read Busha, Van Deske, and Rajagopal's paper review. So everybody remembers this picture, and I won't really explain it. I just have it here to set the stage. So it introduces in particular the coordinates in which boost invariant flow is best expressed. So the symmetries. So this is usually stated as a set of symmetry assumptions, which boil down to the statement that the energy momentum tensor is a function of the proper time alone. So you ignore the dependence on the transverse coordinates at this stage. We will come back to that later. But you ignore the transverse coordinates. And you also ignore space-time rapidity, which is denoted by y here, annoyingly. And so the eigenvalues of the energy momentum tensor depend only on the proper time. And there are actually 3, not 4, because the symmetry around, isotropy or homogeneity in the transverse plane means that 2 eigenvalues are the same. So there's a longitudinal and a transverse pressure and an energy density. And yeah, something's happened, but that's okay. So okay, great, thank you. So I will also, another assumption, which is not, physically realized really, as you know, is conformality. So this is a simplifying assumption. Actually, Jean-Paul Blaison, in his talk 2 days ago, he mentioned some things that happen if you relax that assumption. I will be making it. Okay, one can loosen it, of course, at the cost of complicating things a little. So I'm assuming conformality. So actually, there are not 3, but just 2 independent eigenvalues, and it is convenient to choose one of them to be the energy density and the other one to be this quantity, which is the difference between the transverse and longitudinal pressures, normalized to the average pressure, which would also be the equilibrium pressure when equilibrium is eventually approached. And so, so this is a dimensionless measure of distance from equilibrium. That's why it's nice to use this. And another technical point, which is important somehow, is that we will most of the time use this dimensionless quantity as an evolution parameter, instead of proper time, where this temperature that appears here is the effective temperature defined through the energy density. Well, in that sense that in equilibrium, the longitudinal and transverse pressure are equal, right? Wave P. No, P is the average. I mean, you can parameterize things in different ways, right? Some people just use PL, right? That's also fine. It's just that to me, I want to see whether I'm close to equilibrium or not, right? And I think this. I mean, certainly this is 0 in equilibrium, right? I mean, this is my energy momentum tensor. So I think I just mean that it's isotropic, if that makes you happier. But yeah, I mean, of course, this is of course not an indication of what the system is actually doing, right? I mean, there are many other observables and so on. So I mean, I'm not claiming anything that you would not claim yourself, I think. Anyway, so this is just a technical point. So then, before you commit to any kind of dynamics, you can make a statement. You can make the following statement. So we believe that in that situation, the energy momentum tensor is conserved. So that gives one equation. And given all these symmetry assumptions, you can write that equation, well, for example, in this way. So basically, this says that the effective temperature as a function of this time W can be calculated, provided you know the pressure anisotropy as a function of that variable. And hmm? Yes, it's just that. Yes, it's just that. So then I'm pointing this out just because we will be asking ourselves where's the information about the initial state in this as time goes on, right? So I mean, you have these nuclei, they're very complex objects. I mean, you can coarse grain them and so on, but there's a lot of information in the initial state. And then some of that information we also see in the final state, in the sense that the spectra of the measured hadrons, they reflect somehow the initial state. On the other hand, you have this business of forgetting many things because you have this, because somehow MIS works, you've forgotten a lot of the complexity of QCD. What's more, MIS itself has, as I will discuss, has a lot of things that it's forgetting along the way. So it's kind of important to ask yourself, where is that, what is happening to that information? So I want to say at this point that this is a differential equation of first order. So there's one integration constant. So for example, in the Bjorken model, A is 0, and this just ends up telling you that the temperature is decreasing according to the well-known 1 over tau to the 1/3 picture law. But if you have some theory like QCD, that theory will eventually produce, if someone can calculate it, this function A of W, right? And then if you integrate this, you get one integration constant. But all the other information about the initial state in this Bjorken picture is connected in whatever theory is responsible for the time dependence of the pressure isotropy. And the point is that in these Bjorken type models, you will get some sort of prescription, maybe a differential equation, maybe something else for this function A of W. And in many of these models, well, actually, I guess in all of these models, at late time, this function tends to a universal locus, right? I mean, tends to 0 along a path which is basically fixed by the shear viscosity. But earlier on, you could think that it does many different things depending on initial conditions, because the initial conditions are so rich. But actually, what happens in many models here is that this function A of W tends to approach a curve that you can determine. And that's what is called the attractor in this context. So somehow this attractor describes a partial loss of memory of initial states through this kind of process. So this was kind of just Bjorken flow, but now we're going to look at two examples. One of them is a very simple one. It's, yeah, the box. Yeah. Yes. So that's what I'm saying here, in fact. I'm saying that in QCD, if you set up a boost invariant initial state, it will, that you can look for a Bjorken flow solution in QCD, and then QCD will produce A of W. We don't know how to get it, but it will produce A of W. That A of W will depend on whatever initial data QCD is able to describe. And then this A of W, I mean, we don't really know this in QCD, but in some models, right, in MIS and kinetic theory, what happens is that this A of W, so there's some theory which tells you what A of W is, and then A of W, at least in these examples that we know, has this behavior, right? So this is not a statement about non-equilibrium statistical physics or anything like that. It's a statement about the specific situation that you have in heavy ion collisions, that you have a boost invariant expansion with a little transverse action at the beginning, right? Well, it would be nice, and I mean, I think in the following talk you will hear some other attempts to look for universality away from equilibrium, which are not even probably not, which are actually not really connected to Bjorken flow at all. I mean, and at the same time, they, I mean, I can comment on this. Excuse me? Yeah, some of them. So in fact, you know, I'm going to be talking about the relaxation time approximation in the context of kinetic theory. But of course, that's a very simple kernel, collision kernel. But people consider more complicated ones, motivated by QCD, and those kernels have the potential, right, to describe universality, which is you know, which is probably relevant for heavy ion physics. And so in other words, the attractors that I'm going to be talking about are kind of boring in the sense of, you know, in the artistic sense. I mean, they're just very boring curves. But you could imagine that that if you were able to account for QCD dynamics, you could see something, you know, something more non-trivial going on at early times, right? So I think in the following talk there will be that will probably be highlighted. Yeah, I'm sorry. Yeah, I try to be. Yeah. Let me. I think the answer to your question is, of course, it would be right. But you know, I can only really speak for the simple things that I've seen so far. But yeah, I think there's potential there. Okay, so when I say MIS, I just mean the simplest variant. So everybody's probably seen this. I'm assuming a conformal equation of state, and I'm assuming eta over S being C eta. So C eta is, let's say, 1/4 pi. And there will be there's this relaxation time, which I'm taking to be conformal. The values of these constants, if I show a plot, the values of the constants are the ones borrowed from n equals to 4, but of course, they could be different. So this example, I mean, I will now speed up. This example that just illustrates it in the most simple way is exactly this MIS theory, where the theory of A of W of what this pressure anisotropy is just a first order equation, and if you solve it numerically, you see what I was describing in words earlier, that you see there's some sort of curve which connects some point here at early times. So this is what Jean-Paul Blaiseau would call what he would call the free streaming fixed point. This doesn't have to be free streaming here, actually, but there is a fixed point of this equation in the sense of differential equations, and this curve starts there, and it ends up somewhere, you know, behind the wall, in very close to equilibrium. And if you plot solutions to this equation, you see that they indeed gravitate toward this curve. And you can also look at the gradient expansion. So I will actually show it on the next slide. You can solve this equation in the gradient expansion, and the leading order will be the Navier-Stokes term, so to say. And that's also describing the attractor, but it's describing it for values of this variable which are, you know, close to 1, whereas there is clearly something going on here also at much earlier times. Okay, and a point that is important to note is that this phenomenon is taking place. I mean, these solutions here, for example, are trying to get on this attractor, even though the pressure anisotropy is, let's say, 2.5, which is, you know, I mean, we can discuss how much of a measure that is, but it is definitely anisotropic, right? The energy momentum tensor at that time. Okay, so the point, so in my title, I said that I want to, well, I suggested that I want to look at this whole set of questions from the point of view of asymptotics. And so indeed, this equation is easily solved in a power series in inverse powers of W. And one, you know, one gets something like this. This is in fact, the gradient expansion of MIS theory for this simple flow. And the important point is here that these coefficients do not depend on initial conditions. So this gradient expansion, which is valid close to equilibrium, is completely universal in this model. There's no memory at all of initial conditions in A. So the only memory of initial conditions that this theory has at late time is the scale of the energy density, which is that integration constant which you get when you solve the conservation equation. Of course, this is a differential equation, so it has to have the capability of describing different initial conditions. And from this asymptotic point of view, that happens because this is not the whole story. I mean, you can also check that if you plug in such an expression into the equation, it will be solved up to higher orders in what is in the parentheses here. And this combination, which follows from the equation, depends on the parameters in that equation. It brings in an arbitrary constant denoted by sigma here, and that is the integration constant of the equation. And in fact, you can continue and you can add something like this squared times another series, and so on. And in that way, you build up a description of any of these solutions from this asymptotic late time point of view. And but there's only one constant. So I say powers of this, by which I mean that this constant sigma is the same everywhere there. So basically, the different possible initial conditions in this picture are captured by different, different values of sigma. And when you look at the picture, sigma is what controls the deviations from the red curve somewhere here, in the middle. Or of course, if you could magnify this plot, you would also see that these curves are not literally on top of each other. I mean, they become very close, so these contributions are exponentially damped in time with a scale set by c tau, which is the relaxation time, which is also the non-hydrodynamic mode frequency of the non-hydrodynamic mode of MIS. Yes. Well, the MIS equation, what I mean by the MIS equation is this: it's a first order equation, right? So the complete equations of hydrodynamics are the conservation equation and this equation. So you have two first order equations. Of course, you can combine them, and then you have a second order equation. C tau is, it's the relaxation time. So if I go back here, right, it's here. I guess that's where is it? Yeah. Yeah. I mean, it's this. How much? How much? I mean, all I'm doing is I'm just taking A equal, let's say, to a constant plus some other constant divided by W and so on. I'm plugging it in and comparing powers, and then that fixes these coefficients. So the 8 over c eta you can see even without doing any calculation, because when W is going to infinity, basically you see everything. I mean, this term and actually also this term goes to 0, and I mean, yeah, A is that's the leading order. A is this, right? And you can kind of iterate. I'm not sure if I'm answering your question, but but I mean, you definitely get an infinite series, right? Because if you plug in just the leading term, it will not satisfy the equation. There will be a discrepancy, right? And you need this higher term. And in fact, you also need that term, right? And you also need, if you really want to be picky, you also need all these higher things. So this is, by the way, called a trans-series sector. It's a nomenclature from people who study this kind of thing. And there is an infinite number of these trans-series sectors. So this solution, it looks complicated, but that's because we started at the far end, right? We started at the asymptotic end, right? It doesn't mean that this is the only way to describe it, right? Numerically, it's very easy to get, and you can also actually get it, by other means. But this asymptotic point of view is good because in heavy ions, we are somehow measuring things at the asymptotic late time end. Okay, I think I haven't been here yet. So there are three stages to this. So there's first this rapid approach to the attractor, then there's this sort of slow stage where the exponential, so this decay is power law. This is exponential, but more with a rate that makes it more gentle. And then finally, somewhere far out, there is an asymptotic stage which is completely independent of initial conditions. So the reason I have this slide is because I want to say that because in heavy ion collisions we do see traces of the initial state, that means that we're not in this asymptotic region where the only dependence on the initial state is through the integration constant of the conservation equation. We are seeing some of these in this language, some of these trans-series corrections, because they carry information about the initial state beyond that scale of energy. I mean, in the Bjorken model, strictly speaking, of course, that's not really true. But if we include the transverse, dynamics, you will see that actually they are definitely observed, and yet they also have this exponentially damped character. Okay. Mm-hmm. No, I don't think so. I mean, so in reality, of course, so the Bjorken model, if it's ever reasonable, it's reasonable at the early time when the transverse dynamics are ignorable. And as time goes on, I mean, there is transverse flow generated. So obviously so the Bjorken model starts, being worse and worse. And hmm? Yeah. I'm not sure there is that much symmetry there because you have anisotropies there that you measure. So I don't know. But I mean, certainly, I mean, when I think about this, I think about this going to the freeze out time, and then I say goodbye to this problem, someone else takes over. So the equation of state, everything changes, right? When the transition, I mean, after the transition. So I'm not sure if one could. I mean, it's an interesting thought, but I'm not sure that. I mean, I don't imagine. I mean, Bjorken flow is surely not. So yeah, Well, I mean, in physics, there's the transition to hadrons, which is completely ignored here. I mean, the equation of state is conformal. So obviously, this cannot really be, good there. I mean, yeah, eta over s is also constant. Bulk viscosity is 0. I mean, there's this is a metaphor. I mean, it's a metaphor. But I think I mean, what I want to say at the end. Yeah, bulk viscosity. Yeah, bulk viscosity. Yeah. Yeah. Yeah, there are where you absolutely, yeah. But I think from the physical standpoint, at least to me, it seemed the most interesting thing would be to understand the transverse dynamics. So let me get there. It's not well. Anyway, I just want to tell you about that. But this is the zeroth order in that kind of thinking, right? So I just want to sum up what we've seen so far. So the gradient expansion, it's an in this model at least. I mean, it's probably more general, but in this model at least, it describes the asymptotic near equilibrium limit. So that what that means is that if you, in this model, if you go to infinite time, you will see that this series, works better and better. Second point, I'm not going to go into this much, but I want to just make the statement that this series has a vanishing radius of convergence, the series itself. So it does not define any function in itself. There are many functions which have that asymptotics, but at the same time, and this I've again allowed myself to to highlight. At the same time, this gradient expansion, it contains all the information about the theory, all of it. In other words, even though it's a divergent series and you can't sum it without doing some fancy footwork, it contains all the information there is. These numbers here, they allow you, I mean, there are ways, if you knew all these numbers, of regenerating, of finding out all of these numbers and so on. In other words, these numbers, which are also fixed by the equation, they are not some sort of independent extra information that you have to supplement this divergent series with. This divergent series contains everything, right? So from these coefficients, you can get everything. Yes, so this is the word the relevant word is resurgence, that there are relations between coefficients in this sector, that sector, and the next sector, and so on. So this is, Jean-Paul Blizot used I really liked his comment that it's that this is, beautiful. It's a beautiful distraction, right? So yeah, there are things that I'm not talking about here today, like resurgence, because from a physics standpoint, they are perhaps a beautiful distraction. One should be careful about and indulging too much. But what I said here is somehow important, right? It is important to understand that the gradient expansion, despite being divergent, contains all the information about your theory. These are not random numbers. These numbers tell you everything what this, in other words, from these numbers, you can learn how many integration constants you have. So if you provide me a series like that, enough coefficients, it's possible to figure out from that how much initial data you can have, and reconstruct the full solution up to those integration constants, those trans-series parameters. Mm-hmm.
This statement, how general does it apply to any or?
Well, the proofs exist for ordinary differential equations. So like MIS boost invariant flow, this is a statement which, as far as I understand, is a mathematically waterproof statement. So people like Kostin and others who work on resurgence, they have proved that nonlinear equations, ordinary differential equations, their solutions are resurgent functions. So these. Yes. So if you have an ODE. Now, there are, these people are working on partial differential equations where theorems exist, but I'm not sure how general they are. So I say that this whole story is a sort of metaphor at this point. I mean, it's true for Bjork and flow. So what I said is true here. Now, how much it generalizes, it's a question of, can you prove resurgence for some other set of PDEs, and I know that for some cases it has been done, but I don't actually know even which those are. So yeah, that's a very good question. So, yes. I don't know. So in fact, I will mention this in a second. When I talk about kinetic theory. Yeah. Mm-hmm. Right, right. It's just that there are no general theorems like for ODs, right? That's what I mean. But yeah, we're all, yeah. But actually, thank you for reminding me. So in the case of n equals for super young Mills, where you can do these calculations in gravity. Yeah. So, but there it has been. So actually, there it has been checked. So checked to at least the lowest, like 3 or 4 sectors. It was kind of checked that these resurgence relations are satisfied, even though the calculation is done in gravity in one higher dimension. There's some voodoo going on before you actually get to this. But still, the series that you get in these sectors, they are related by resurgence, as one would expect from an ODE. Okay. So so that's the important point. So yeah, so the chance series, which is the full thing, it contains now the initial data, all the initial data, and each sector can be obtained from the gradient expansion. Okay, so now Berta. So this is the Boltzmann equation and the relaxation time approximation. So this is what Jean-Paul Blaiseau was talking about. It's exactly the same system. The only difference is that I'm focusing, I'm focusing on the conformal case where the relaxation time is like 1/t with some constant gamma, which actually can be scaled away or put equal to 1, so it doesn't appear anywhere else. And so here people have looked at attractors by various means, and I want to focus on this sort of asymptotic viewpoint, how to study them. And I will follow the approach of that Jean-Paul Blaiseau was presenting, where he looked at a specific set of moments which are somehow tailored to this problem and allow for some analytic progress. So you saw 2 days ago that these moments Ln, they satisfy an infinite hierarchy of coupled ordinary differential equations. And for what I want to do, it will be more convenient actually not to use these moments, but rather their ratios. So the benefit is that these now are dimensionless. So Professor Blaiseau, he emphasized that these are all of the same, they also have the same dimension. So these are now dimensionless. And the first one is just the pressure isotropy up to that factor of -1/3. So then you can translate the hierarchy of equations satisfied by these L moments into these M moments, and you can play the same game as he did. So you can say that let's truncate it at some level n. So let's set all the moments to 0 for n greater than some n. And when you do that, you get a nonlinear ordinary differential equation of order n-1. So for example, at level 2, which is what Jean-Paul Blaiseau was considering in his talk, he had this equation for G0, and G0 is roughly the pressure isotropy up to some rescaling and shift, constant shift. So he had some equation. This is that equation written in the language that I'm using, and this looks very much like the Israel-Stewart equation that we looked at, the MIS equation that we looked at, with the one difference. So there is, let's see, what is it? This one, I think. This one, yeah, this one. No, this one, the 10 here. So basically, in MIS, you just have a term W times A, right? And there's no term which is just A, right? So this is a sort of Israel-Stewart equation, but it is not. It's actually not the same as the MIS equation. It doesn't make any difference at late time, but it does change things at early time. So at level 3, you can again do the same thing. You get some other equation. Now this is second order, and you can go on if you want. So these are now, so this way you reformulated this RTA Boltzmann equation in the RTA approximation. You have it in a form of equations where you can apply the same kind of analysis that we saw in MIS. Yeah. Okay. Thank you. I see. So you have this term. Yeah. Anyway, so this is different, right? So this is different. I mean, it's almost MIS, but it's not MIS. It's a little bit different. Thank you. So yeah, so I won't, of course, do that. I just want to say a couple of things about these equations. So you can. Yeah, okay. Or you could, I'm not saying I'm saying this because I don't want to be. Okay, but so I would say that this shows that that it's not the proper one because it doesn't get you to hydro because hydro is MIS, right? So, but it is the proper one if you want to study the dynamics of kinetic theory. No. No. Sorry. Yes, you caught me offside. You're right. No, I don't want to use. I try to. I try to educate myself to use hydrodynamics to mean the gradient expansion. So yes, so I mean the MIS. Yeah, I mean the NMR is not MIS, but the NMR is the one that pops up, that comes up where you when you try to study kinetic theory. Yes. Well, wrong from the perspective of kinetic theory, right? But kinetic theory in itself is a very limited sort of theory, right? No, it's not. It's not hydro. I'm sorry. No. That's not. No. When I say no, I'm sorry. When I say I'm trying to stop, but when I say hydrodynamics, I mean MIS. When I say, but I try to use the word hydrodynamics to mean the gradient expansion. So that's what I think. I mean, I've struggled with this like everybody else, right? Sometimes when you say hydrodynamics, you mean one of a number of things. So I think, yes. So I didn't use that phrase according to that guidance. Yes, MIS is hydro only in the hydro domain. Yes, and the NMR is hydro only in the hydro domain. So close to equilibrium where the gradient expansion. Excuse me. Yes. Absolutely. So all these, yes. So DNMR, MIS, and other yes theories. They all coincide near equilibrium. Yes. Uh, yeah, first of all, I think this is probably not a question for me because I mean, I of course am aware of the NMR, but I haven't really studied it that much, so I probably can't answer. But I mean, the coefficients I wrote here are definitely the ones that come out of this calculation, and I'm willing to take your words for it that they're the same. But it's not the coefficients that are the most important. The most important thing is that MIS just doesn't get you that this term, the term which is which if you normalize the derivative like this, there's a term which has no w in front, right? It's linear in a. I mean, because okay. Mhm. Yeah. Okay. Well, thank you for these comments. So I just wanted to say something about the equations you get at every order. I mean, of course, we haven't checked every order, but quite far, further than you'd think. So for each of these equations has a pre-hydrodynamic attractor. That's the first statement. The second thing is that the stable fixed point at the origin approximates free streaming precisely in the way that Jean-Paul Blaiseau was explaining in his talk. So basically, the magic value is the pressure isotropy equal to 3/2, and it starts being 1.4 maybe at level 2, and very slowly it approaches this magic value 1.5 3/2. So that's this point. Then here now you can calculate the gradient expansion from this or from this, and what you find is that the gradient expansion comes out correct at level n. You get n terms that are right, but the following terms are wrong. So if you are interested in this distraction of actually studying the large order behavior and trying to see where kinetic theory is really different from MIS, for example, then you really want the high order terms. So actually none of these truncated equations is really great for that. Yes, you can, let's say at level 10. Okay, so the gradient expansion in any of these equations is divergent. Now, the terms, they depend on W, so the question is like at what value of W do they start growing, right? I can't really tell you. I can tell you later, but it's you don't have to wait a long time. You don't have to wait to 20 or 30. I mean, it's But anyway, I'm not sure that's. I mean, the point is that the term depends on W, right? So if you evaluated W equal to 1, it'll be somewhere where it starts growing. If you evaluated W equal to 1/2, it'll be somewhere else. I'm not sure it's a yeah. Well, if you truncate, well, what I mean here, I mean you get an equation of order at order 9, right? So if you truncate at level 10, it's a the degree of the not degree, the order of the equation is then 9, right? And it'll get the first 9 terms correctly. And when I say correctly, I mean because that you can compare this with a calculation directly in kinetic theory, right? And so in kinetic theory, you can, people have calculated, in fact, one of them is here, also calculated this series. And so you know what is right and what is wrong. So if you truncate, you get the hydrodynamic, the corrections to the hydrodynamic end to some point. But when you go to like earlier times, these equations will break down. And of course, these series have, just like in MIS, vanishing radius of convergence. Okay, so this paper, actually I have it here. In that paper, we wanted to calculate these series on a gargantuan scale, and for that, using these ODEs is not really practical. But there's a clever thing that you can do, and that is you can introduce a generating function for these moments. So introduce some other variable x and just package all the moments into such a thing. And it turns out that this equation, this function satisfies a partial differential equation, which you can derive from these equations that Jean-Paul Blaiseau was showing. And this PDE can then be solved in various ways. In particular, I mean, it can be used in various ways, and what we did was to use it to generate very efficiently this gradient series to high order, but also to generate an expansion for small. Yes. So M1 is the pressure isotropy, and then the higher ones contain high derivatives. So then the thing that I think is sort of interesting is that So having that made us think of looking for solutions actually not in inverse powers of W, but in powers of W, so for small w. So this is around early times. So such a series is convergent. And actually, because it's a convergent series, it actually defines a function, and that is the attractor of kinetic theory. So basically, people have characterized it in various ways. Some numerically, there are various approaches, but this is somehow, I think, the sort of cleanest, in that you generate a convergent series around 0. And if you go far enough, that series tells you a lot about that, kinetic theory. So what I have specifically in mind is that if you take that series, so this is now I'm using the equality sign, because this is actually, this sum is convergent, defines a function for some region in the W plane. And you can, this has a finite radius of convergence. And what's more, you can check that the singularities, you can check that it's possible to analytically continue this function, which is defined by the series close to 0. You can continue it to arbitrarily large W. And when you do that, what that means in human language is that you fit a rational function, a Padé approximant, to this series. And then when you have the rational function, you can expand it, for example, around W infinity, if you like, right? And that's what we wanted to do, because then we can compare what we get here with what hydrodynamics tells us. And in hydrodynamics, we know from from the gradient expansion, we know that the leading behavior, the asymptotic behavior of the pressure anisotropy is 1 over W, and the coefficient is 8 times the eta over S. And this coefficient is very close to what we know to be the shear viscosity of RTA kinetic theory, which is 1 over 5. So basically, so this is a kind of, I don't know, we found it satisfying that this comes out. Okay. Mm-hmm. Yes. Yes. Okay, so this series is I mean, the pressure I saw, well, okay, so we're looking at this is moment M1, right? So right, that's what this is. So we're not actually looking at the other moments at this point. So if you wanted to, it's one number, yeah, it's one number, right? This moment is one number, but what's more, this is the attractor, so that number is not actually for you to choose. It's it's 3 halves in case of A, and it's like minus a half for M1, right? It's a fixed number. Well, I'm not sure about other kernels. I mean, with other kernels, I'm not sure how far you can get with, yeah. So, yeah. I don't think it's an artifact of Bethe in the sense that I think, to the extent that in kinetic theory, free streaming is an obligation, right, at early time. This value where this starts out, that's the pressure anisotropy which corresponds to free streaming, which you can calculate directly from the Boltzmann equation. So I think for the attractor, there is no, and you know well that the attractor has a well-defined initial condition. You can't play with it. Now, the other So if you start off the attractor, then of course you can do what you like, but that will involve higher moments. Yes. I'll go a little longer. 5 minutes, 4 minutes. Yeah, I don't have that much left, so, and I have a chance of actually making it in time thanks to the generosity of the organizers who give an hour. And I can never make it in 45, but but an hour. Okay, so transverse dynamics. So yes, as we discussed at the beginning, the symmetries of Bjorken flow are so restrictive that you don't really get much interesting physics. And so the question arises, can one somehow build on this model? Because this is a valuable insight into the problem, I think, the Bjorken model. But of course, you have to extend it if you want to get some real physics out of it. So the observation that initially the transverse flow is negligible opens up the idea to treat it as a perturbation, for example, at the linear level, which is what I will talk about. And so this allows us to address two questions. One is the stability of the attractor. So this is not a I mean, it is worth asking that question because, for example, if you take ideal fluids and take the Bjorken solution, the 1 over tau to the 1/3, then try to perturb it by including transverse directions, that perturbation will just grow as a power law indefinitely. So the linear approximation will be invalidated. So there it doesn't work. I mean, perfect fluids, the attractor is just A equals 0 all the time, right? The pressure isotropy is 0 all the time. So that's the first question, and this is possible. Yes, for this there is an answer. And then the other one is, well, at the linear level, your expectations may not be high, but you would somehow like to see that that flow is, observed. That this approximation will give you something, right? So some non-zero V2, for example. So I will quickly just go over what I have in mind. So so this is Xinan and me. So you basically say the temperature is the some Bjorken solution, but we can easily take just the attractor because the error we make will be very small after some initial transient. We perturb the velocity, the shear stress tensor. Then it's convenient to work with normalized modes. So these delta t hat in real space and delta pi hat in real space are dimensionless. Once you go to Fourier space, these fields, so phi could be this or this or yeah, this is not dimensionless anymore, but in real space they're dimensionless. So you take the MIS equations that you saw earlier. So in the end, you end up with 6 coupled ordinary differential equations for every mode, right? So if you say I want to look at a mode with fixed wave vector, you have a 6x6 system of differential equations, and then you can solve the first. You can do like we did with MIS, with the boson variant MIS. We first look just at numerical solutions, so that's enough to see, at least get some feeling for whether the attractor is stable. So what is plotted here is the ratio of delta T hat, the perturbation to the temperature, normalized by some value at the initial time, right? So this is like the relative, this is basically what happens. Is it going down or is it going up? So what happens is, so this is when you initialize on the attractor. And what you see is that there's a quick drop and then sort of more moderate sort of fall off with oscillations. And if you initialize somehow off the attractor, then the drop is actually much more significant, and you still get this kind of fall off. So this is basically a kind of some numerical evidence that that it's actually stable in that sense. That this setup of linearizing around Bjorken flow, even though it doesn't make sense in ideal fluids, it does seem to work in MIS. And then you can, once you have, I mean, someone who has what's the word? For someone with a hammer, everything looks like a nail, right? So you have a system of 6 ordinary differential equations, and with time dependence, you want to see what is the late time behavior, right? So that's what we did. So this, I think, I would, maybe this is maybe this qualifies as a distraction, but anyway, so you can try to find the asymptotic behavior, and sort of written here. So, for example, for this delta t hat, this perturbation, there are no power law contributions. This is all exponentially suppressed, and there is 1 plus dots. So there's some infinite series here. But if you just take the leading, this prefactor, right? You also get some amplitude, because this satisfies a linear equation. So each of these solutions comes with some kind of amplitude. But what you can do is you can take a numerical solution and you can fit this amplitude to it, just to see if this form captures the behavior at late time. So the parameters that appear here are listed here. So some of them, so this one, for example, is what we saw for perturbations of Bjorken flow, which they did not depend on transverse dimensions. So this is what we had before. But now there are other ones as well. So there are some other ones. They involve this MIS asymptotic speed of sound. Also, there's something that looks like a frequency here, but it's not really a frequency because it depends on tau. There's actually, so it's something like this. So that, you could add subleading terms, but actually those subleading terms you can put into those subleading terms. But this one you have to keep because there's a tau in front of the omega. So in front of the omega, so tau times, I mean, this contribution is actually growing. So it's like a non-perturbative contribution at large tau. But anyway, at very large tau, this goes to some kind, it goes to what you would expect. Omega is, the speed of propagation times k. And these numerical solutions, which are just the ones we saw before, just now normalized differently, it's kind of amazing that this relatively simple asymptotic formula reproduces this pattern. This works better for higher k, of course, than for lower k, and it also shows that the perturbations of higher wave vector are damped more than the ones of lower wave vector. So this is the rest of the numbers that appear there. So the main point, the somehow maybe, I don't know if it's surprising, but important, I think, point is that these perturbations there, they are damped exponentially and in time, but these perturbations, they contain all the physics of heavy ions in this setup, right? So if you want to look at the flow of this MIS fluid, right? If you want to look at that flow from the perspective of Bjorken flow perturbed by, by some transverse thing, all the physics that freeze out depends on, comes in through these exponential corrections. So you can you can try to go through this exercise to calculate flow coefficients, and I've written these formulas here just to show that they're so this thing is actually, well, anyway, yeah. So what this shows is that if you know what these linearized perturbations are doing, you then have to integrate them over the transverse plane, basically, and so all these contributions, all these averages, they are these exponentially suppressed things, and you get something, and the painful thing, the sad thing, I would say, is that to calculate these things, you need to invert the Fourier transform. So you have to reassemble. So like if you have an initial condition, you can, of course, Fourier transform it and set initial conditions for these perturbations. But then at the end, you can calculate, let's say, numerically how the modes have evolved. But you still need to invert the Fourier transform, and that we only knew how to do numerically. So this is not really an analytical result, but you get something. So first of all, yeah. So you get even with these values of these transport coefficients that we were using, you do get elliptic flow around 0.1 integrated V2. A question which worried us a little bit was how sensitive this is to the relaxation time. And we saw in the talk by Matt Lusum that what the Jetscape calculations show is that the dependence is small, and you can see for yourself by going to this Jetscape widget. I don't know if everybody knows, but I learned of it from Matt Lusum, and I could see for myself that indeed when you vary the relaxation time by a factor of 2, it looks like V2 goes down by a factor of, it's not a factor, sorry, by maybe a few percent, less than 10%. So in this calculation with the linearized perturbations, that sensitivity is between 5 and 10%, so it's like a little bigger. So, but in any case, it does at a qualitative level, it kind of works. Okay, so I've pretty much finished. So to summarize, I'd say that these early time attractors are a window of opportunity for hydrodynamic models. In other words, these hydrodynamic models like MIS, DNMR, and so on, they're not hydrodynamics, but because of this attractor business setting in due to probably boost invariance, there is a window of opportunity for these models to explain things. Secondly, asymptotic methods are, in my opinion, essential kind of tool to understand what is going on from a sort of semi-analytic point of view. And finally, I think this is kind of weird sounding, but physics at freeze-out is captured by these exponentially suppressed corrections to the Bjorken attractor, right? So of course you can say that maybe the Bjorken attractor is not what you should be thinking of as the most important thing here. But if you try to understand these flows from that perspective, then yeah, you end up with this statement. Thank you very much for the good questions. I mean, they depend on the non-hydrodynamic sector, yes. I'm not sure, to be honest. I mean, the non-hydrodynamic sector is necessary to regulate, stability and so on, right? In this framework, I don't know. So if you're thinking about the density frame, I don't know. No, you're not. No, I don't. It's hard to say what are the wider implications. I mean, one thing that would worry me would be if the dependence on the relaxation time was really significant. I think it's a little more than I'd like to see, but it's only a linearized approximation, so I can easily believe that it can be improved. Thermodynamics. You know, I mean, I was I was using all the time this conformal equation of states. So you know, I didn't really probe the possibilities of instabilities arising from thermodynamics. I'm not sure if I'm answering the question, but yeah, I'm not sure I can really say something useful. Yes. Yes. Well, yes, because also the relaxation time appears there, right? It's tau over tau r, basically. Yeah.
Which makes one explanation. And will have some non-academic curves that then the main right?
Right.
That would be interesting to check. Changing beta into a beta with the relaxation time of lambda and then one is to adjust things properly to make the load and see whether the non-hydrodynamic part of the story anchors the main.
Yeah, that's actually a really nice idea. Yeah, I think that should be entirely doable along, using, for example, this moment approach or even directly maybe. Yeah, I think that's a very cool idea. Thank you.